Hello everyone, and welcome to the 9th lecture of the Introduction to Media Engineering course. So in the last weeks we finished the topics of video and animation. In this topic we here today, and most probably the next lecture as well, we will talk about compression, because as we said before, compression is very important when it comes to storing digital media. Okay. So we are going to cover the compression of different types of media, as we will see. So compression must, as we said, must often be applied to digital multimedia to save actually storage space. There are, if you remember this slide from before, there are two types of compression methods. We have lossless compression, we have lossy compression. So lossless compression is as follows. If you have some original data, you compress it, you get the compressed data, and then if you decompress the the compressed data, you will get back the same original data without losing any of the content of the original data. Example of this is like zip compression, which we apply to any files. The other approach is the lossy compression, and in lossy compression, if you have the original data, you compress it, you get the compressed data. If you decompress the compressed data, the decompressed data would be slightly different from the original data. And the good thing is that slight difference is not something noticeable to us, and this is most suitable for images like JPEG compression or audio like MP3. Okay, so we are going in this lecture, we're going to discuss different types of both of lossless compression and lossy compression. We'll see how it's done in images, how it's done in video and audio, and so on. Okay. So the data compression process actually passes through a number of stages. So first of all, you have your input data that you want to compress. First stage is called the encoder, which actually compresses the data. And then once the data is compressed, either it will be stored on the computer or it will be transmitted over a network. Now, to be able to play or display that data, you need actually to decompress data. And this is done using a decoder. Okay, so we have the encoder that does the compression and the decoder that does the decompression. So actually the encoding decoding algorithm, the one that compresses and then does the reverse afterwards, is called the codec, where the COD comes from the encoding and the DEC comes from decoding, so you get the term codec. So sometimes when you try to play a video on Windows Media Player, for example, might say you don't have the required codec. So what is the codec that you don't have? It means that you don't have the algorithm or the API or the library that can decompress that video or compress it if you want to compress. Okay, so let's see the different examples of the compression methods. So we start first with lossless image compression. This is the first topic that we are going to talk about. So consider the image that's given here. And you remember we had this actually before, this image. So if we are going to use bitmap to store that image without any compression, and if the image is of a square of width 45 millimeters, and let's assume we're using 24 bits for each pixel at a resolution of 72 pixels per inch, if we multiply these numbers by each other, we get 48 kilobytes. So this means you can store that image without any compression using 48 kilobytes. Now, can we do some compression? And we're not talking here about vector graphics. We're talking about still storing the image as a bitmap, but in less number of bits. So one idea is that this image can be stored in less space. How? If the first row, let's assume the first row here, consists of 128 pixels. All of them, they have a blue color. So we can actually store that information in only 4 bytes. How? We will use 3 bytes to store the color. So if it's RGB, R would be 0, G would be 0, and B would be 255. These are the 3 bytes. And then 1 byte to store the number of pixels that have that color. So if you think about this, we were able to store that given that all pixels have the same color, so we're only storing the color and the number of successive pixels that have that color. only 4 bytes, okay? Compared to what if you were going to store this as a bitmap. Let's assume again this is 128 pixels. Each one will be represented in 24 bits or 3 bytes. Then you're comparing now 128 multiplied by 3 bytes compared to just 4 bytes for the whole row. This is a significant reduction in the number of bits that are needed to store that information. At the same time, this is lossless, because if you think about this, once we have those 4 bytes, we can easily draw or determine the colors of the pixels on the first row without losing any of the content of that row. So this is a technique that is called actually run length encoding, as we will see in the next slide. So what is run length encoding? Run length encoding, or RLE, is the technique of replacing a run of consecutive pixels of the same color by a single color value and a count of the number of pixels in the run. So we're trying to replace consecutive pixels that have the same color with the value of the color and the count of the number of pixels. So let's see another example for binary images. In binary images, we only have black and white pixels. So the RLE version, or run length encoding version, that we are going to discuss now, that's applied to binary images, there are multiple versions, but this one can do actually good compression by only representing the locations of the black pixels. So one thing about binary images, the pixel is either black or white. So if you represent the locations of the black pixels, then by default the other pixels are white. So there is no need actually to represent the white pixels. And this is actually what is done here. Okay. So how are we going to do that? So this is actually how it's done. So for every row of black pixels, or that includes black pixels, you indicate the column number of the start of the run. The run here means the consecutive pixels that are black, and the column number of the last element in the run. So let's see the code. So this is for this image. Let's look first at the component of row number 4. So row number 4, we have black pixels starting at column 2 and ending at column number 6. This is how it's written. 4, the row number, 2, the start of the run. We have consecutive pixels from column 2 to column 6. So 4 to 6. Now for row number 2, we have start of the run at column 1 and end at column 4. So we have 2, 1, 4. And for row number 1, now row number 1 is different. It's like you have 2 runs of black pixels. This is the first run and this is the second run. Why these are 2 different runs? Because a run has to be consecutive black pixels with no white in between. So we have here 2 runs. The first run, so we write first the row number 1. The first run starts at column 1 and also ends at column 1. That's why it's written here 1 followed by 1. First element, last element. And then on the same row, we have a run that starts at column 4 and also ends at column number 4. So we have 4 followed by 4. And in between the elements of different rows, we have actually brackets to indicate a separation here. So now if you think about this, how many bits do we need here to represent that information? So first of all, this image was actually, this image is 8 by 8, right? If it's a binary image, then each pixel would be represented by 1 bit. So in total, this needs 64 bits, right? Okay. Now let's count how many bits do we need to represent the run length code. Okay. Now, if you think about the numbers that could be present here, the smallest number is 0 and the highest number is 7, whether you're talking about the row number or the column number, the beginning and the end, right? So the smallest number that you can put is 0, the highest is 7, which means that to represent the numbers, you would only need 3 bits, okay? So how many numbers do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is like, okay, we have 11 numbers, And given that we are representing each number in 3 bits, so we're multiplying by 3, this is actually 33 bits. So this is a significant reduction from 64 to 33. But there is one more thing that's missing here, which is how about the brackets? Because according to this code that we wrote here, the brackets are essential to differentiate between where the data of one row starts and ends. Okay. If you add the brackets into the different symbols that could appear, you have actually, as we said, we have numbers from 0 to 7. So these are 8. The 9th symbol would be actually the left bracket, and the 10th symbol would be the right brackets, as if the bracket will be represented in a binary code. In that case, now you have 10 different symbols that could appear, which means that now you need 4 bits. Now, how many symbols do we have in the code? We had 11 numbers, and then in addition to this bracket and this bracket, now these are 13, 14, 15, 16, 17. So in total, we have now 17 symbols multiplied by 4. This would be more accurate than this, okay? 17 multiplied by 4, this is now 61 bits. So instead of representing the image in 64 bits, you now have 61 bits. Someone might argue that, okay, you're only saving 3 bits by doing that. Yes, that's true, but it depends on the image. Like, imagine if this image was bigger than that, for example. Or actually, let's imagine another situation. Imagine that this row was all white. Okay, so you'll be saving 1, 2, 3, 4, 5 symbols will disappear. So now instead of 17, you have now 12 multiplied by 4. So the whole thing about run length encoding is that whether this one or the example we had in the previous slide, by only representing the successive pixels that have a certain color, like here in black, then actually you are saving. And the effectiveness of such method depends on the image that's being compressed. So imagine an image where, like, imagine here in this 8x8 image, if it's like the checkerboard or the chessboard, so black, white, black, white, black, white. Definitely that image, if it's represented with run length code as we explained here, will have a bigger size in terms of the number of bits than just representing it as a binary image. So the whole thing, it depends on the image. In some images, you will be saving a lot by using run length encoding, and in some others, you wouldn't actually save. You will be wasting space. Okay. In any way, this is actually one example of a lossless compression technique, because as we said, if you have the code, you can easily draw the image and you're not losing any of the content of the image by using that code. Okay, so this is the run length encoding. Okay, so the next method that we want to discuss is called the Hoffman coding. And Hoffman is the name of the person who proposed that method. So we say that if you have a bitmap image, and if we have 256 colors, then each pixel is normally represented by 8 bits, as we already know. Now, the idea of Hoffman coding is that compression could be achieved if colors that appear more frequently are assigned fewer bits than those who appear or that appear less frequently. Okay, and this is what we call variable length code, that we're not going to assign to each color 8 bits constant. No, those colors that appear more frequently, we will assign to them less number of bits, while others will be assigned more number of bits. And this is the basic idea of Hoffman coding. So to explain the idea, let's see an example. And let's assume an example that's not text. That's not images. We're not talking about images. Let's assume we have text representation. And let's assume that someone would like to store or send that message. Okay? This message has 5 symbols, which are this symbol, this one appeared like 3 times, this symbol, this one, and this one. Now, if you're going to represent this normally, then what you will do is the following. Since we have 5 symbols, then how many bits do we need to represent them if we use the normal binary representation? If you have 5 symbols, then you need actually 3 bits. So one way is to say the following. I'm going to assign to that symbol the code 000, this one 001, 010, 011, and 100. Okay, so based on this is not variable length code. This is what's called fixed length code, giving each symbol the same number of bits. Now, how many bits do we need now to store that message? Given, let's count how many we have. We have how many total number of symbols? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 symbols, and each one is represented with 3 bits. So in total, you need 30 bits to represent that information. Okay? So far, this is not compression. This is just the fixed length code. Okay, so now if we see another way of representing the symbols, then one can use actually what's called this dictionary. So let's see how this is represented. Now, this symbol, the triangle, let's assume we're going to give it a code of only 2 bits. Why? Because the triangle appeared, if you check the message, it appeared 1, 2, 3 times. It has the highest frequency. In addition to this symbol also appear 3 times, so you also will give it 2-bit code. This one that appeared twice, we're giving it 2-bit code, and these ones that appeared, each one of them appeared only once, we're giving them 3-bit code. Now, regardless of how we obtain that table, this is what Huffman coding tries to do, but let's examine. If we have this representation, someone was able to put together this table. So if we have that representation, then how many bits do we need to represent the message? So let's see. So this symbol appeared, as we said, 1, 2, 3 times. So the frequency here is the number of times it occurred, appeared 3 times, each one 2 bits. So we have 3 multiplied by 2. We need 6 bits to represent that symbol in total. This one appeared 3 times, 2 bits, 3 by 2. This one appeared only 2 times with 2 bits, so 2 by 2. This one appeared once with 3 bits. This one once with 3 bits, so plus 3 plus 3. In total, we have 22 bits. Compared to what? Compared to 30 bits that we had in the previous slide. So if you use fixed length code, you need 30 bits to represent the message. If you use the variable length code as obtained by Huffman coding, you need only 22 bits. So you're saving 8 bits out of the 30. This is like almost 25%, okay, which is a big reduction. How? By doing this idea that those symbols that appear more frequently, we are giving them longer codes than those that have actually shorter or appear actually less frequently. Okay, so Huffman coding is about obtaining this. Okay, now this was only about text. Now how about images? So for images, colors appearing more frequent will have shorter codes in the dictionary. So to map this idea to how we can deal with images, then this is what we are going to do. Instead of the symbols, we will assume that the symbols are just the gray levels. And those gray levels or colors that appear more frequently, will give them shorter codes. And those colors or gray levels that appear less frequently will give them longer codes. And that's how we can compress an image. We will see how this table could be obtained for a certain message. However, there is another approach called the Limpel-Zeven-Welch or LZW. This is a variant of Huffman coding that constructs this dictionary optimally. But let's forget about that for now. We're going now to focus on Huffman coding in the next slides and the algorithm or the method that given a certain number of symbols, a certain symbols with their frequencies, how can we find the code? Okay. Okay, so let's have an example. So consider a data set that has 6 symbols and their corresponding probabilities. And by probabilities here, we mean the percentage of the data that has this symbol. So for example, if we assume that those symbols represent certain gray levels in an image, then what's the percentage of pixels that have those gray levels? So let's see this example. Let's say we have the symbols A2, A6, A1, A4, A3, A5. Now each one of those A's could be a certain gray level, like this could be 255, this is 128, this is 100, and so on. And what's given here is the probability. So like the gray level, let's assume A2 is the gray level 255. So the gray level 255 appeared in 40% of the pixels of an image, so it's 0.4. A6 appeared for 30%, A1 10%, and so on. So the first step in doing Huffman coding is to sort the symbols in descending order according to their probabilities as shown in this table. Now, once we do that, once we have the values sorted, the next step would be to apply the Huffman coding algorithm that we will see actually next. Okay? So let's do it here step by step. So I'm gonna write one more time the table that we have, because this is the beginning of solving this problem. So we have A2, A6, A1, A4, A3, A5, and we have here 0.4, 0.3, 0.1, 0.1, 0.06, and 0.04. So this is how it goes. You start, after you sort them descendingly as done here, you start with the last two elements, the lowest two probabilities, and you add them up. So when you add this one to this one, 0.06 plus 0.4, you get actually 0.1. Okay? Now, when you add the last two elements, you have to resort the list one more time. Now, given that 0.1 is already the smallest value, so we just put it at the end of the table, and the rest will be the same. So this is the same 0.1, same 0.1, 0.3, and 0.4. Now you do that one more time, you add up the last two elements, so 0.1 plus 0.1, you get here 0.2. Now, one thing here, if you resort, the 0.2 wouldn't be actually the lowest value. So let me erase that. In fact, the 0.2 would come here, and this 0.1 would be here, and then 0.3, and then 0.4. You actually keep doing this until you reach that you have only two elements left, and then we will see what would be the next step. Okay. So now we have 0.1, 0.2. If you add them up, you get 0.3. So the summation can be at the end of the list, 0.3, 0.3, and 0.4. Now when you add up the last two, 0.3 plus 0.3 is 0.6. So we put here 0.6, and this 0.4 would be here. Now that you reach the end where we only have two elements left, you start assigning binary codes starting from the last two and then going backwards. So given at the end that we only have two values, then we need just one bit. In that case, the code here would be 0 and the code here would be 1. Now you go backwards. Now the 0.4, the number 0.4 that we have is the same as the 0.4 that was at the top of the list in the previous level. So the value 1 would be the code of the 0.4, while the 0.6 that we have here is coming from the summation of these two elements, okay, from the 0.3 and 0.3. So the 0 in that case will act as the beginning, or what we call the prefix of the code of these two. So both 0.3 and 0.3, their code will start with 0, okay. So let's write that here. So 0, I'm gonna write it here, okay, 0 for this 0.3 and 0 here. Now to differentiate between the 0.3 and the other 0.3, we add one more bit. So this would be 0, 0, okay, and this would be 0, 1. So this is now the code for the 0.3, and this is the code for the other 0.3, 0, 0, and 0, 1. And then when we go back one more time, the 0.4 is the same as the 0.4 in the previous level. So here the code is 1, the 0.3, this 0.3 is the same as this 0.3, so the code of 0.3 is 0, 0. So the code of this 0.3 also would be 0, 0. So we have here 0 and then 0. And the 0, 1, which is the code of the other 0.3, this 0, 1 is the beginning, will be the beginning of the code of these two, of the 0.2 and the 0.1. So we write here 0, 1, and we write here 0, 1. Now to differentiate between them, we add a bit here that's equal to 0, and we add a bit of 1 here. So this now is the code of these two. Now going backwards, the 0.4 again is the same. So this is 1, this is 0, 0, and then the 0.1 that we have here, this 0.1 is the same as this 0.1. Its code is 0, 1, 1, and therefore the code of this 0.1 would be 0, 1, 1 as well. So here we have 0, 1, 1. While the 0, 1, 0, which is the code for the 0.2, the 0, 1, 0 will act as a prefix for these two. So we have here 0, 1, 0, 0 and 0, 1, 0, 1. Okay, going back one more level, here this is the code is 1, this code here is 0, 0, taking the code of the 0.3. The 0.1 in the previous level was 0, 1, 1, it's the same 0.1, and then this now is 0, 1, 0, 0, and the last value, which is 0.1 here, that has a code of 0, 1, 0, 1, its code will be prefix for these two, and therefore we have 0, 1, 0, 1, 0 and 0, 1, 0, 1, 1. Okay, now this is actually the end of applying the Huffman coding. Now a couple of things to note here is that first of all, you can see that symbols that have high probability of occurrence, like A2, which has a probability of 0.4, has the shortest code, a code of just 1 bit. While A5, which has a probability of 0.04, has a code of 5 bits. So this is the whole idea of Huffman coding, that those symbols that appear more frequently are given shorter codes than symbols that appear less frequently. Okay, so this is one important note here. So of course, it's not like Huffman sit here and brought a piece of paper and just tried this and got this randomly. There is a mathematical proof behind Huffman coding, okay, but we don't need to go into that. But this is actually the algorithm. So if you are implementing this method, this is what you will need actually to do. Okay. Okay. So this is what Huffman coding is. So this is actually what's written here. So we saw step 1 before. So step 2, combine the bottom two symbols, the least probabilities, and repeat this process until you have 2 remaining symbols only, as we did in the previous slide. Step number 3 would be to code each reduced source, starting with the last level and going backwards, which is starting from the last 2, we're giving them the code 0, 1, and so on, until we reach the beginning of the data. Okay. Okay, so now given that this is the algorithm of Huffman coding, then how much saving do we get by doing this? So let's make an assumption. Let's assume we had an image that had actually 100 pixels. Okay. Now, given that we have 6 different symbols, then how many bits do we actually need to represent the 6 symbols in that case? If you have 6 symbols, let's assume that these symbols represent the gray levels, then of course, if you consider this to be a grayscale image, you would need 8 bits to represent each pixel. But let's assume we're not going to do that. We're going to use the shortest fixed length code that we can assign to 3 symbols. So if you have 3 symbols, you will need, in that case, actually 3 bits per symbol, right? So in total, if I have 100 pixels, and each pixel would be represented with 3 bits. So in total, you need actually 300 bits to represent that image. Now, let's see if we use Huffman coding, how much saving do we get? So again, assuming that we have 100 pixels, now the symbol A2, let's assume symbol A2 is representing a certain gray level. This one appeared in 40.4% or 0.4, sorry, of the pixels, like 40% of the pixels. And that symbol has a code that's just 1 bit. The symbol A6 or the gray level A6 appeared in 30% of the pixels. It has a code of 2 bits long. This one, 10%, 3 bit long, and so on. So let's count. So for A2, we have 40 pixels, each one represented with 1 bit, plus for A6, we have 30 pixels, each one would be represented with 2 bits, plus for A1, 10 pixels, multiplied by 3 bits, plus for A4, another 10 pixels, multiplied by 4 bits. This is the length of the code, plus 6 multiplied by 5, plus 4 multiplied by 5. So if you count how many these are, we have 40 plus 60, this is 100, 130, 170, 200. This is actually 220 bits. So now it's like if you use Huffman coding, you represent that image with 220 bits, while if you use the regular fixed length code, you need 300 bits. You're saving 80 bits in that case. Another way of representing that same piece of information is here we made an assumption that we have 100 pixels, right? However, we can compute a number that represents the same idea without knowing how many pixels we have. And that number is called the average number of bits needed to represent each symbol. We obtain L average by multiplying the probability, in that case was 0.4, multiplied by 1 bit. So instead of 40 by 1, we just multiply the probability by the length of the code. 0.4 by 1 plus 0.3 by 2 plus 0.1 by 3 and so on. So we get actually 2.2, which is the 220 divided by 100. So this is 2.2, so which means that per pixel you need 2.2 bits on average. Of course, there is nothing called 0.2 bit, right? But this is an average number. Yeah, sometimes you use 1, sometimes you use 2, sometimes you use 3. On average, you have 2.2, which means, again, if you had 100 pixels, you need 220 bits. Now, that L average, in the case of not using Huffman coding, the regular actually binary coding, you will be multiplying each probability by 3. Okay? So you will get here 3. So it's like you're comparing 2.2 to 3. It's like you're saving 0.8 bit per pixel. Okay? So this is actually how much saving we get by doing the Huffman coding. Now, another important thing about Huffman coding, other than its ability to save in terms of number of bits, is a very important property, which is that the resulting code that you get from Huffman coding is uniquely decodable. What do you mean by uniquely decodable? Means that if you look at the code that is generated for any piece of data from Huffman coding, there wouldn't be any ambiguity. You wouldn't be confused what this code represents. So let's have an example. Let's assume I'm gonna write the numbers here, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0. Let's assume this is the code for part of an image that was represented using Huffman coding according to the table that we have below. Now let's start decoding. As we said, in any compression algorithm, there is the encoding and the decoding, the compression and the decompression. So in the decompression, you have the binary code that's now shorter than the regular code, and you would like to decompress. You would like to know what this string of binary bits that we have here, what do they represent in that case? So starting with the first bit, which is 0. So what you will do, okay, you read the first bit, it's 0. You go to the table and check if any of the symbols have a code of single 0. When we look down here, so there are actually, the first one is 1, so definitely this 0 is not representing A2, but the 0 here could be representing A6 or A1 or A4 or A3 or A5, because all of them start with 0. Okay, so but the 0 itself is not sufficient, so therefore we will have to read one more bit. So we read 0 and then 1. Now, do we have a symbol that has a code 0, 1? Actually, this excludes A6 because A6 is 0 followed by 0. So it's either A1 or A4 or A3 or A5, one of them, but still we don't know. Now let's add one more bit. So 0, 1, 0. Do we have any symbol that has the code 0, 1, 0? You look here, it's not A1 now anymore, so therefore we're excluding now A2, A6, and A1. It's either A4 or A3 or A5, because all of them start with 0, 1, 0, but we still need to read one more bit. We read the next bit, which is 0, 1, 0, 1. Now, if you look down here, 0, 1, 0, 1, so there we are talking about either A3 or A5. The next bit will determine, and given that the next bit is 0, then that tells us that now this is actually A3. Okay? So as you saw, once we reach the 0, 1, 0, we're done. So because none of the other codes has this code 0, 1, 0, and more importantly, none of the other codes starts with 0, 1, 0, 1, 0. Let me clarify this in the next one. So now this is A3. We go to the next bit, which is 0. Okay, so we have a 0 here, which is that 0 here. Again, this excludes A2, could be A6 or A1 or A4 or A3 or A5. We read the next bit, it's 0, 1. 0, 1 could be A1, A4, A3, A5. We need the next bit, which is another 1. Now 0, 1, 1, this is definitely A1. Why? Because as you can see, A1 has the code 0, 1, 1. And none of the other codes, A4 or A3 or A5, starts with 0, 1, 1. So once you reach 0, 1, 1, you are 100% sure that this is the symbol A1. This is one important property of Huffman coding, that none of the codes that you will get is a prefix of another code. So for example, A2 starts with 1, right? You will never find any other code starting with 1. Okay, so this is one important property of Huffman coding. None of the codes is a prefix of the other code. Okay, I'm gonna explain this one more time after I finish this example. Okay, so let's continue with the example. So 0, 1, 1, it's A1. Then the next bit is 1, right? So this 1 here. Okay, now this 1 here, this is definitely A2, right? Because A2 has a code of 1, and none of the other codes start with 1. The next bit is also 1, so this is also A2. The next bit, this one, it's 0. Okay, this could be any of the other 5. We read the next bit, which is 0. So 0, 0, this is definitely A6. Okay, so that's the code. So as mentioned here in the example, this code corresponds to one message only, which is A3, A1, A2, A2, A6. Now, why do we need the codes to have this property that none of the codes is the prefix of another code? Because let's imagine another situation. Let's imagine that A2 had the code 1, and for example, A3 had the code 1, 1. And let's assume you had a message that's equal to this, 1, 1, 1. Now, if you try to decode 1, 1, 1, and A2 has the code 1, A3 has the code 1, 1, where this example, A2, the code of A2 is the beginning of the code of A3. This is violating Huffman coding, but let's see what will happen if we have a code that violates the idea of Huffman coding. Now, 1, 1, 1 will have actually multiple solutions. It's either A2 followed by A3, So the first one is A2 and the last two ones representing A3. Okay, or let me erase all of that. This is one option, or it's A2, A2, A2. So each one of the ones is A2, or it's A3, A2. So there are three different solutions. Therefore, you wouldn't be able to decide if you have a code of 111 and you have a dictionary that says that A2 has the code 1, A3 has the code 11. You wouldn't be able to determine what's the original message. You will have ambiguity. Okay? So this is a very nice property about Huffman coding. This will never happen in Huffman coding. In Huffman coding, none of the codes will have, or none of the symbols will have a code that's a prefix of another code. Okay? So if you're solving this by hand in the exam, for example, and you end up getting a case where you have a symbol that has a code, and that code is the beginning or the prefix of the code of another symbol, definitely you did something wrong, because Huffman coding will never result in this. So you have to repeat your calculations. Maybe during going from one step to another, you made a mistake. Okay? So this is a very nice property about Huffman coding, and this will guarantee that whatever code that you will get, you will be able to decode it in one way only. Okay? All right, so one other note about Huffman coding, let me clear this up, which is when the number of symbols to be coded is large, the constructing Huffman code is not efficient. This is one issue with Huffman coding. You see, this example that we did had only 6 symbols, like as if it's an image that has only 6 gray levels. What if the image had 50 different gray levels? Can imagine how big that table would be and how hard would be constructing it. So therefore, there are other variants of Huffman coding that have been proposed that are more efficient in terms of obtaining them. They are near optimal, meaning that they are not as good as Huffman coding. We're not going to go into that, but you will see that in other courses in the future. Okay. Okay, so this is the idea of Huffman coding, and now the main difference between Huffman coding and run length coding is run length coding that we explained before was trying to represent the repetition of colors on the same row using a short representation. Huffman coding is different. Huffman coding is trying to represent the repetition, but it doesn't care if that repetition is on the same row or not. Like if a certain color gets repeated a lot in the image, we're giving it a short code compared to a color that appears less frequently. So the concept itself is different, but both of them are lossless, because as you saw here, if you have this code, you will get the exact symbols or message that you wanted to represent from the beginning. Okay? All right, so this is all about Huffman coding. So we next move to lossy image compression. So we talked already about lossless image compression. We talked about run length coding and Huffman coding. So lossless compression that we talked about can be applied to data types such as text and executable programs where the corruption of one bit invalidates the whole data. So in general, you can apply lossless compression to images, but it wouldn't give you a lot of compression advantage compared to lossy ones. However, we cannot use lossy compression with text or executable programs. Why? Because lossy compression, as we said, will make a little change in the content. So imagine that you are saving the character A and then like compressing it, and then when you decompress it, you get B, for example. So this doesn't make sense. Same thing for executable programs, like changing one bit will corrupt the whole program. So lossy compression algorithms cannot be used with text or executable programs. However, they can be used with images, because we say here that images, however, they can tolerate some data loss that would be invisible to the human eye. This is the whole idea. We can play a little bit with the gray levels of an image if that, or the colors, a little bit with the colors, if that will make us save in terms of storage. And this is the basic idea of the JPEG compression. JPEG stands for Joint Photographic Experts Group, the name of the group that invented that method. And this is the most commonly used lossy compression method for still images. It's best suited for photographs. So let's see how the JPEG compression works and how it actually changes a little bit in the image in order to save in terms of storage. So let's see what's the basic idea of JPEG compression. So first of all, any image can be considered as a three-dimensional function with x and y coordinates define the pixel position, and the z coordinate represents a height that corresponds to the color. So let us take an example. Let's say we have this image, this cameraman image. So this image can be represented in 3D by having this to represent the rows, this dimension represent the columns, and then the third dimension here represents actually the gray level. And a pixel that is bright will have a high value on this z-axis, while a dark pixel will have a low value on this z-axis. So you look here, this is the bright gray pixels. They are, as you can see, they are at a height different from the dark gray pixels of the grass. The zero, the cameraman, the zero would be actually at the bottom of this figure. So why is that important? Because as can be seen in this figure, the edges are represented as steep slopes in the height figure. So first of all, what are the edges? Edges in any image, these are the boundaries between, for example, an object and a background. An area or a location in the image, the edge is a location in the image where the color changes in a sudden way. Like for example, if you look at the cameraman here, like the border of his shoulder, this represents the edge. Why? Because here we have a gray color and here we have black. So in between, this is an edge. Okay? And as you can see on this three-dimensional figure, locations where edges are, they represent steep slopes, like places where the color is dark gray and suddenly goes to light gray. Or here, this is a dark gray and then suddenly goes down to black. So the edges, they represent in this figure steep slopes. Why is that important? We will see that next, but let's go with this for now. So now we reach the conclusion that edges in an image represent steep slopes, places where the color changes in a sudden way. Okay? So these actually steep slopes, they represent high frequencies in the frequency domain representation of the image. So remember before when we talked in the beginning of the course about frequency domain representation, and you remember that when we talked about images, that images also can have frequency domain because let's first talk about the idea of steep slopes and high frequencies. So let's have some examples. Let's say we have, forget about images for now. Let's say you have a signal. This is time, and this is some signal that looks like this. Okay, so this is a sine wave. Now, this could be another sine wave that has a higher frequency, right? Now, compare that to something that looks like this. Now, the bottom one represents actually zero frequency. Why? Because there is no change. This represents a low frequency, and this represents a higher frequency, right? Now, compare that to something that looks like this. A place where the value was something, and then suddenly it goes up to another value, and then continues constant. In fact, this is, if you compare this to this is quite like the opposite. Like this is a no change at all. And here, this is a sudden change. It's not like even a gradual change as you can see in the sine wave. This is actually a sudden change in the value from very low to very high. That's why we consider this figure to have a very high frequency, because the change happened in zero time. It's not like something gradual, or here, this is zero change. So now let's compare that to what we had in the image. So we said edges in images represent places where the color changes in a sudden way. So it would be something very similar to this, right? Like imagine this was the the cameraman, who is like in black, and this would be, for example, the sky. So you had a very dark value here, and suddenly you have a bright value. Okay. So edges in images, given what we explained so far, then these steep slopes that we saw in the three-dimensional figure, they represent high frequencies in the frequency domain representation. Now, the good thing about these high frequencies, and this is now the main idea of JPEG compression, is that high frequency information can be discarded from an image without perceptible loss of quality, because people do not perceive the effects of high frequencies in images very accurately. Our visual system as humans is not that sensitive to changes in the high frequencies, not like the changes that happen in the low frequency areas. Okay, so if you have a low frequency change, you will notice it. But if you have a high frequency change, playing with that high frequency change a little bit wouldn't matter. You wouldn't actually notice that change. Okay, so given that property, the people who thought of the JPEG compression, they said, okay, given that, let's do this. Let's try to identify the frequencies that are in an image, and we will play a little bit with the high frequencies, given that people are not actually sensitive to the high frequencies. Let's play with them a little bit to our benefit so that we can store the image in less number of bits, and we will see how we can do that. While the low frequencies, we will keep them as they are. But in order to be able to do that, you need some tool that can take an image and compute its frequency domain representation so that you can easily identify the low frequencies and the high frequencies. And that tool, as we will see now, is called the discrete cosine transform. The discrete cosine transform is something very similar to the Fourier transform. It's actually trying to do this. It has the same objective. Like the discrete Fourier transform tries to find the frequency domain representation of an image, the same thing like the discrete cosine transform. So how does it work? If you have an image like this one, this would be the outcome of the DCT. So let me explain what this actually is in the next slide. Okay, so apart from the mathematical description of discrete cosine transform that you will see in other courses later on, let's just talk about the concept. So if you have an image, let's say this is an image, okay, and let's assume this image has a sine wave that is traversing that image in the vertical direction, okay? How? Like, for example, this value here is white, and then this could be gray, okay, and then this is black, and then you go back to gray, and then white, and so on. So this is like a sine wave, right? Because if you imagine it, it's like having 255 and then 128 and then 0 and then 128 and then 255 and so on. Like this would be another 128 and so on. This is like you have a sine wave that's traversing this image in the vertical direction. Okay, so horizontally there is no change on each row. There is no change in the color, but vertically you have like a sine wave. Okay, so if you take that image and apply the DCT, the discrete cosine transform, what you will get is a matrix that has the same size as the image, but the difference is the axes now are not representing pixels. Here, this we can call it fx, like the frequencies in the x direction, and this is fy, the frequency in the y direction. Let's assume that this sine wave had a frequency of 5 Hertz. Okay, then the discrete cosine transform of that image, what will happen is, because your frequency is appearing vertically, then this value, okay, this value here, which is the value 5, will be bright. It will have a strong value. Why? Here, this is your origin. This is your 0 and 0. Okay, here, this is your origin. So this is like the 0, 0 frequency. Now, as you go further from the origin, whether to the right on the fx direction or down on the fy direction, you're increasing the frequency. So if that image has a single frequency of 5 Hertz, then you will have a high value at 5 Hertz here and nothing else in the rest. The rest would be just zeros. Okay? Now let's have another example. Let's imagine the image has changed a little bit, and now the image is consisting of a sine wave that is traversing the image in the opposite direction. Like, for example, this would be white, this is dark gray, this is black, and then gray, okay, and then white, and then gray, and so on. So this means that vertically there is no change. The change is only on the horizontal direction, right? So you have a sine wave horizontal. In that case, let's assume also the frequency here was 5 Hertz. So in that case, we wouldn't have this value here. Again, this is your origin. Your value would be around here. Why? Because you have a frequency that is on the horizontal direction, and that value would be at 5 Hertz. So you have a high value representing the power of that frequency at 5 Hertz. Now, what if the image is not like horizontal or vertical frequencies? What if it's something like this? It's like a sine wave traversing the image diagonally. So this is actually what you will get. Let's again assume this was 5 Hertz. You will have a bright or a high value at this value. Why? This value is representing, now this value is not on the x-axis or the y-axis, it's diagonal. Why? Because now this sine wave is traversing diagonally. So you have a bright value here. Okay? So this value, this point, represents the frequency that appears in that image. How about the other bright values that you might see here? Actually, these are just the harmonics. You remember when we talked before about frequency domain representation and so on, we said that the harmonics of the frequency also appear like twice, triple, and so on. So all of these are just the harmonics. You can just ignore them. This is the most important one, the first bright value. Okay? Now, why is that important? Because as we said, the idea of the JPEG compression, we want to eliminate the high frequencies, right? So we need a tool that can identify the frequencies in images. So if you take an image and apply the discrete cosine transform, you get its actually frequency domain representation. Now, where are the high frequencies in this domain? The high frequencies would be around this area. Again, this is your 0, 0. This is the no frequency. The high frequencies are here. So any bright values here indicate that you have high frequencies in that image. And these are the high frequencies that we will try to play with in order to save in terms of the storage of the image. Okay? So again, the DCT, similar to the DFT, it's a tool that can identify the frequencies in an image that we are going to use in order to identify those high frequencies and then reduce their values somehow. Okay? So this is the procedure of the JPEG compression. Images are divided into 8 by 8 pixel squares, each of which is transformed separately using DCT to reduce the computational complexity. So if you have a big image, you will divide that image into blocks. Each block is 8 by 8, and for each separate block, you compute the DCT. And then applying the DCT itself actually does not reduce the size of the data, because the array of frequency coefficients that you will get as an outcome of DCT is the same size as the original pixel array. So if you have an 8 by 8 block, you do DCT for it, you still get 8 by 8 values. So where is the reduction? Where is the saving in terms of storage? So the DCT step itself is not the step that is going to reduce the size of the image. It can just identify the frequencies, and then later on we apply this. So since high frequencies are explicitly separated, we can identify them in the DCT, as I said, in the bottom right corner, or in like the right and the bottom areas of the domain, then they can be easily discarded or given fewer levels in quantization. And this last thing is what is used in JPEG. So we are not aiming to completely eliminate the high frequencies. You cannot do that, because now the edges might be completely gone and you don't want to destroy the image that much. Okay, but this is what we do. So if the value produced by DCT for each frequency ranges from 0 to 255, this is what we do. The lowest frequency coefficients can have any value from 0 to 55. They will keep their original values. The slightly higher frequencies might only have values that are divisible by 4, and the highest frequencies might only have the value 0 or 128. So what does this mean? So let's see what this means. So let's imagine that this is the output of the DCT. Okay, so this is what we will do. We will divide that domain into 3 areas. For example, areas that have low frequencies would be here. Areas that have slightly higher frequencies would be here. And areas with very high frequencies would be, why would be the remaining part? Because this is our origin. This is our 0 and 0. And fx increases in that direction, fy increases in that direction, right? So this is what we will do. This area, the values in it will keep their original value. So if the DCT gives you some value, you will keep it as it is. So the values will be from 0 to 255. This area, the values would be only divisible by 4, like 0 or 4 or 8 or 12 and so on. Now, what if the DCT obtained for a certain frequency here a value equal to 3? What you will do is that you will re-quantize the data. So the 3 is closer to the 4 than the 0. You'll assign it to 4. What if I have a value of 7? The 7 is closer to the 8 than the 4. We'll assign it to 8 and so on. So by doing that, you are actually using only values that are divisible by 4. This means that how many how many levels that you can have in that case. Originally you had 256. Now you only have 0, 4, 8, 12 and so on. So only values that are divisible by 4. It's like instead of 256 values, you will have only in that case, if you count how many of these we have, okay, you will find that you have 256 if you divide it by, this is like 2 power 8. If you divide that by 4, you get 2 power 6. You'll have only 64 possible values, meaning that for these frequencies, you will need only 6 bits to represent their values, because they will be either 0 or 4 or 8 or 12 and so on. Okay? Okay, so that now this is for the area. Now for the highest area, the high frequency areas, you will have the value either 0 or 128. Now 0 or 128. Now what if the DCT obtained the value of 10? The 10 is closer to 0 than 128. You will replace the 10 with 0. What if you have a value of 200? The 200 will be given 128. So this is of course the error here. The difference between the actual value the DCT obtains and the value that the JPEG will store is big. Okay, but what are we gaining by doing this? That only now we have only 2 values, which means that you only need 1 bit to represent those frequencies. Okay, so overall it's like this, the low frequency area, you will need 8 bits to represent any frequency here. You will need 6 bits to represent any frequency here, and you will need 1 bit to represent any frequency here. Compared to what? That you would have actually used 8 bits for all of them. Okay? Now, this step is a lossy step. Why? Because if we do that, if you replace one value for the high frequency, let's say that that value was whatever, it was 10, it was 15, and you replace it with 0. Now, the original value is gone forever. You are storing the 0, as there is no way it can go back from the 0 to the original value that was 15. So that's why this is a lossy compression technique. But the amount of saving is high in that case. Okay? So this is the main idea of the JPEG compression, is that you can now store the DCT, you will be storing the DCT coefficients, but after re-quantizing them or changing their quantization according to this mechanism, that will result in saving a lot in that case. Okay. There is actually one more step left for the JPEG compression, but I'm gonna postpone it to the next lecture. I just want you, before we leave this lecture, to see the example. So this is the original image on the left, and this is the image that has been stored with JPEG and then decompressed. So what do you notice here? You see, like this area, and this area, they are very similar. These are the low frequencies area. There is no change in that area. This is a low frequency area, and therefore that's why it's not significantly affected by JPEG compression. Now look at the edges, because this is where the JPEG will be changing. Look at this area here, like look at that edge and look at it here. This is the original without any JPEG compression, and this is with the JPEG. You can see there is a significant difference around the edge area between this and this. However, from a distance, you might not actually, these are like zoomed in versions of the images. Okay, from a distance, you might not be able to see that. Okay, you can even try it yourself. Get an image that is saved as BMP, bitmap, and open it in Paint and save as JPEG, and look at the difference. You will see a difference between the two images. Look at this here, this area here. This is a high frequency because there is white and then suddenly it's blue. Compare it to this one, there is a distortion that happened. Okay, but from a distance might not be that big. Okay, all right, that's it for today. I'm gonna stop here, and we'll continue that in the next lecture, inshallah. All right, I'll talk to you soon. Goodbye.